breaker for protecting the devices, because the circuit breaker has to carry the fault current. So we'll see some problem that way. So meanwhile, let's quickly review what we have done in the last class. So actually I could not put up the PDF of the last class, but I can just quickly show you what we discussed in the last class, and then from that we will continue. So just give me a minute. I'm opening. So you can see the 3-bus system on your screen. We have bus 1, bus 2 and bus 3, and then we have the impedances from the two generators, G1 and G2. So the question was find the Z bus. So basically this is a review of actually Z bus building. So what we did, we went through two methods. The first method is find out the Y bus and then invert the Y bus. So that is a method A, and method B is step by step. So first I found out the method A. So you can see on the screen the reactance diagram we converted into admittance diagram. So this J4 has become minus J2.5 and J0.8 has become minus J1.25 and so on. So this entire circuit I converted into admittance network. From that admittance network, we are able to create the Y bus. And once we have the Y bus, I simply invert the Y bus and then we calculated the Z bus. This is a very straightforward method. But here the problem is inversion of the matrix is involved. So that is the computationally that is a big problem. So the next method, building Z bus step by step, we had seen. So first step, I have taken the reference ground. From the ground I have added the bus 1. So whatever is the impedance, that is J0.2, will be the matrix. Then in the second step, separately I have taken bus 2 and then connected to the ground, and there the impedance total was 0.4. So my Z bus will be size is 2 by 2 matrix, where I have 2 rows, 2 columns. So the second row, the off diagonal elements will be 0, and then J0.4 was added. Then in the step 3, you can see in the diagram. So this was step 1, this was step 2. In the step 3, I am adding an impedance between 1 and 3. So in that case, you copy the column 1 and you copy the row 1, and then for the diagonal element, you take the 0.2 and then plus add the 0.4, then you will get the 0.6. So this is the case 3 of Z bus building. Then in the step 4, what we have done, we have added an impedance between bus 1 and 2. This bus 1 and 2 both are old buses. So when you add two impedances between two old buses, that is a case 4. So for that you need to find out ZLL, which is nothing but Z11, Z22 plus ZB minus 2 Z12. So that we have done here. And then finally I am getting J0.4, J1.4. So then I also taken the second column and first column and then subtracted. So this is the delta Z, and then finally using this formula we calculated the Z bus nu. Anyway, I'll is coming after the that is coming after the 4 iterations. Then in step 5, I am adding another impedance J0.4. Here you can see in the diagram between bus 2 and 3, a new impedance J4 is added. So again, because it's between column 3 and column 2, I take the subtraction of third column and second column, and then I did all these things. Then we have done a MATLAB code, and from MATLAB code I found the Z bus to be this. And you notice this Z bus is exactly same as the one that we built by using Y bus inversion method. So two methods giving exactly the same amount or same value of the Z bus. So this was the first problem, first part of the previous lecture. Then what we did, we started symmetrical fault analysis and then study the effects of three-phase faults. So symmetrical faults are line to line to line to ground faults, or there could be only line to line to line fault also. That also counted as a symmetrical fault. In the symmetrical fault, the point is that all three phases will carry the fault current and they will be equal. So, but then such faults are very rare. Only about 5% of the faults are of this nature, that is triple line to ground fault or triple line fault. Even though they are rare, the fault current is very high. Therefore, it is important to understand symmetrical faults in order to determine the circuit breaker capacity and so on. So we'll see that. Okay, so the generator, I talked about this subtransient reactance of the generator, transient reactance of the generator, and synchronous reactance of the generator. These are three different reactances. The machine is same. The same generator, it will offer three different types of reactances at t different times. So below 100 milliseconds is this, more than 100 milliseconds is this, and these are all again approximate times. These milliseconds will keep changing. So the moment the fault occurs, we get this subtransient reactance. Slightly after few cycles, we get transient reactance, and under normal operation, we get synchronous reactance of the generator. So subtransient reactance, transient reactance, and synchronous reactance. The first one is used for stability and transient studies. Second one used for fault studies. So for determining the current immediately after the fault, you can use XD double dash, and for determining the circuit breaker fault interruption current and all, you can use XD dash, and so on. So with that brief introduction, we looked at one very basic problem, that is a single generator, and then it has a subtransient reactance or transient reactance of 0.1 per unit, and there's a voltage and the fault impedance also is given. So the way we solve it is considering a Thevenin's voltage here of the pre-fault voltage, and then fault current is coming, and then from that I get the fault current, and 6.66 per unit is the fault current with minus J, and post-fault voltage and all we calculated this way. All right. So now let's go back, and what we did, we once again revisited the same question, and now we are asking the question: what if there is a fault at bus 1? What is the fault current? What if there is a fault at bus 2? What is the fault current? And what if there is a fault at bus 3? What is the fault current? Like that we try to analyze. So assuming that there are some assumptions which are being made, V1, V2, V3 are 1 per unit, no load on the network. So if there is a load in the network, then the voltages at 3 buses would be different. So for that, what we do is we run the load flow analysis of the circuit, and as a result of the load flow, we'll know what are the voltages at all buses, and then that's what we'll be using. Then we have shunt impedance that is neglected, resistance is also neglected. So we have taken three cases. Case A is bus 1 fault, case B is bus 2 fault, and case 3 is bus 3 fault. So here is a diagrammatical representation. Suppose there is a fault at bus 1, the fault current will come from first generator in this path. The current from the second generator will come like this. This is one path, and this is the another path in which the fault current will flow. So the total fault current will be addition of the currents in all these three paths. So we need to find out the Thevenin's equivalent. So for Thevenin's equivalent, we did some simple circuit simulations or circuit calculations, and finally I got Thevenin's equivalent as 0.16, and then fault current is minus J 3.125 per unit. So this is about the first case. Now for finding out the generator currents, we can do current division rules and so on. So let me go to page 4 now. Bus 2, then again we go back to the same circuit, again we do some circuit simplifications, and finally find the Z22, that is Thevenin's impedance at bus 2 and all. So and here the fault current happens to be 2.5 per unit with minus J, and then finally we also calculated the voltages. Now finally in the last case, bus at fault 3 is slightly more complicated because there is a delta to star conversion of impedances. So once we do that, again we get Z33. So one important thing that we understand by comparing the Z-bus matrix which we calculated in the first half of the lecture with the Thevenin's impedances at bus 1, bus 2 and bus 3, we notice that the diagonal elements of Z-bus matrix are nothing but the Thevenin's impedance of that at that bus K. So at that respective buses. So for example, 0.16 is the Thevenin's impedance appearing at bus 1, 0.24 is the Thevenin's impedance at bus 2, and so on. Okay, so with that brief review of the previous class, let's jump to today's lecture. You can try at the end of the textbooks, you have these chapters and you have practice problems. You try to solve these problems, you will learn a lot by solving your own things by solving on your own. So that's the best way to learn this kind of subject. So you can have a, uh, I think you better to use a computer to code and all these things. So anyway, so let's get started with today's problem. And this problem I am taking from the textbook of Hadi Sadar. So this is problem 9.1 from Hadi Sadar's textbook, Power System Analysis. So you can find, you can choose any good book to get the problem. So here is a problem which I find slightly interesting for us to solve. So the problem is like this. I'll draw the consider the following power system. So the power system is like this. There is a generator, and this generator is protected by a circuit breaker and connected to a bus bar. There is another generator, also the same structure. Then connected to the same bus bar is a transformer. So this transformer, of course, we'll have another bus bar here. It has a transmission line. So transmission line also has circuit breakers at either end. And then finally there is a bus bar here. So the impedance of this line XL is 160 ohms. So I can put the J because it is XL. So this value is not given in per unit, it is given in actual impedance in ohms. So all the time we are seeing per unit reactances, but suddenly here you are getting ohms. So here is where you remember your previous lectures on per unit system, and we will have to determine that. We will do that. Now here we have a transformer. The reactance of the transformer is 16%. So that means 0.16 per unit. But then the base rating for this is 100 MVA and 30 by 400 kV ratio. That means if I number the buses, so let's say this is bus 1, this is bus 2, and this is bus 3. So the voltage ratio is 30 by 400 kV. So that means the bus 1 is 30 kV and bus 2 is 400 kV. So we have a step up generator. Alright, so let's come to the generators itself, and then I'll write down the data for the generators. The first generator is rated at 60 MVA and its voltage rating is 30 kV. So that's a good thing to know because the voltage rating matching with the transformer. So then I have XD dash is nothing but 24%. Similarly, for the second machine, slightly smaller machine, 40 MVA, and it has 30 kV rating, and then XD dash is 24%. So this is the ratings of the generator that are given. So what is the question? So the question is like this. Determine fault current when fault occurs on bus 2 or bus 3. Okay. So the fault has occurred on bus 3 here. So at the time, what is the fault currents? So that is the question. Let me also read some assumptions. So the question is saying, initially it is on no load with generators operating at their rated voltage with their EMFs in phase. The rating of the generators and transformers and respective percentage reactance are marked in the diagram. So that's what we get. All resistances are neglected, and then the line impedance is J160 ohms. A three-phase balance fault occurs at the receiving end of the transmission line. Determine the short circuit current and short circuit MVA. So what we have to find out, determine fault current or short circuit current and determine short circuit MVA. So we'll come to this. So this is the question given to us. So what is the first step we have to do? So first step is, you notice that here it is 100 MVA, whereas here it is 60 MVA and 40 MVA. So they are not on the same base. So therefore this 24% reactance cannot be included in the same circuit with the 16% reactance. So we have to do the change of base. So naturally, because the highest MVA is 100 MVA, we'll choose 100 MVA as system base MVA. So therefore S base is 100 MVA. So this is the first step that you need to do. So I hope we are clear up to here. So once I have chosen the 100 MVA as base, then the reactance I have to transform to the new MVA. So what happens is, in this case the 100 MVA is base and 400 kV is the base voltage for, okay, so let me write that. So base voltage for transformer and line is 400 kV. So if I choose it like this, then base voltage for generator, so will be 30 kV. So that is it. So this is the second step. So this is the first step, this is the second step. Now what happens in the third step? Third step, I will calculate the per unit impedance of the generator 1. Per unit impedance of the generator. So in fact there are two generators. So here I'll say generators. Both generators is 30 kV. So what you have to do is, we will use the formula or Z per unit new is equal to Z per unit old multiplied by V old by V base old by V base new square into S base new by S base old. So this was our formula, if I'm not, if I'm correct and if I'm not wrong. So this is 24% and this is 30 kV by 30 kV. So this is nothing but 1. Now S base new is 100 and S base old was, for generator 1 it is 60 MVA. So from this calculation I will know what is the impedance of the first generator. So that reminds me, I'll just open my calculator to do that. So I'm doing the calculation, 24 into 100 by 60. So I get 40. So this is ZG1. Now what about ZG2? ZG2 will be again 24% multiplied by 30 by 30 square. This time it will be 100 by 40 MVA because that's the rating of the second. I'm sorry. Yeah. So here I'll get 60%. So now I have everything in this. So let also calculate Z base for the line. What is that? It is V base square by S base. That is 400 kV square divided by 100 MVA. So that will be 400 by 400 square by 100, because kV and MVA will cancel. This is V by A. So here I'll get, I think 1600 is the 4 square is 16, 4 zeros, 2 zeros will cancel. 1600 ohms is the Z base for the line. So therefore Z per unit for the line, because it is J 160 ohms divided by 1600. So I'll get 0.1 per unit. So J 0.1 per unit. So I think now I have done all the per unit calculations. So this step actually is basically conversion to system base. So what happens next? Now I once again draw the diagram. So but this time I'll do the reactance diagram. So step 4 is reactance diagram. So I get like this. There is a generator and then there is a generator reactance. In fact, I need not show the generator. I can directly show the reactance of the generator. There is another generator, or let me show the generator also. So this is G1, this is G2, and two reactances. Then I have the transformer. Then I have the transmission line, and so on. And here is the fault. So this is bus 3, this is bus 2, this is bus 1. So we got this as 0.4 per unit, J 0.6 per unit. This is J, let me check that. %16. J 0.16 per unit, and this is J 0.1 per unit. So now the next step is just simply find out the Thevenin's impedance. So ZTH so there is a fault here. So the next step is find ZTH, or in this case Z33 I have to find the impedance at bus 3. So you short circuit the generator and then find out the Thevenin's impedance. So here J4 and J6 are parallel. So J4 is parallel with J6, J.6, and then that is series with J0.16, that is series with J0.1. So this is my total impedance. So 0.4 and 0.6 combination, I think it is J, let me calculate that, 0.4 into 0.6 by 0.4 plus 0.6, that is 0.1 itself. So that is 1.0 itself. So I get 0.24 plus J 0.16 plus J 0.1. Now if I add this, 24 plus 16 is 40, 40 plus 0.1, 50. So J 0.5 per unit. This is the Thevenin's impedance. So once I got this, now no information is given about what is the fault impedance. So assuming Z fault equal to 0 ohms, that means it's a dead short circuit. So I can find the fault current. So I fault is nothing but 1 divided by, because this 1 is the pre-fault voltage, so divided by the Thevenin's impedance J 0.5. So finally I get the minus J2 per unit of fault current. So this is about the fault current that we are having here. So now, but then what is, see, this is in per unit. So I want to calculate what is the value in amperes. Okay. So fault current in amperes. If that is a question, how do we find? So it is very easy. So you know that V base is 400 kV for the transmission line, and you know S base is 100 MVA for the transmission line, and this is a three-phase system. So in a three-phase system, you will get the, so you get root 3 VL IL equal to, or root 3 V base I base equal to S base. So from this I will get the I base as 100 MVA divided by root 3 into 400 kV. So V will cancel, this kilo will cancel the mega, and 1000 will come here, and these two zeros will cancel these two zeros. So finally I'll get 1000 by root 3 into 4. So let me do that. 1000 divided by square root of 3 into 4. So I get approximately 144 amperes. So this is base current. So therefore, if the fault current is, I fault is minus J2 per unit, so that is nothing but minus J2 into 144. So that will be minus J 288 amperes. So our magnitude of the fault current is nothing but 288 amperes of fault current. So this is how we can calculate the amperes. All right. The twist is the MVAs are different. So we had to convert everything into common base and then get the reactance diagram. So that is the calculation we are doing here. And once you get the reactance diagram, I can find the Thevenin's equivalent impedance, and from Thevenin's equivalent impedance I can find the fault current. So this ends the first question that we have discussed today. Just a little bit of formula. Okay, so how to find post fault voltages? So this is the question. So what is the post fault voltage? Post fault means after the fault. So before the fault, the pre fault voltages when the system is normal are obtained by load flow analysis. So you can do load flow analysis, and then you can do whatever, Gauss-Seidel method or Newton-Raphson method or fast decoupled load flow method, whatever load flow method you apply, and at the end of that load flow method you will get the pre-fault voltages before the fault. Now what happens when there is a fault? So when there is a fault, in fact, what is a fault? What do you mean by when fault? Fault means when there is a fault, insulation of the system breaks down. So that means a high voltage component is short circuited to a low voltage component. So typically the low voltage component will be the ground. So whenever a high voltage component is short circuited to a ground, then immediately the ground voltage will get affected to that high voltage part. So as a result, the post fault voltages tend to decrease. So that means, so let's say if V pre-fault, let's say it is 0.99 per unit, then this is just example. So V post fault can be 0.23 per unit. So sudden decrease in the, so it will say like 0.99, suddenly it decreases to 0.23. There will be some transient. So this is V in per unit. This is time. So there is a fault at this time. So suddenly the voltage will fall. So that is what we are seeing. But then the question is, how do you calculate? What is the voltages that you get it? So for this, let me just explain a simple situation. So consider this is your network. So the network is completely described by the Z bus of the network. And there are buses. So this is one bus, this is another bus. These are all buses for the network. And you all know that there is a ground bus. Without the ground bus, the Z bus cannot be defined. So you have various buses. So this is bus 1, 2, and so on up to bus N. Now you select a particular bus. So let's say this is the bus K. So I'll write it here. This is bus K. So bus K, there is a fault, and that fault is connected to the ground. So immediately what happens? So the fault impedance is ZF. So what is the current flowing out of this bus? So whatever was the Vk before fault divided by Z fault will be the I fault. So this is that much I fault will be there. But here I have to use the minus sign because the fault current will be going out of the network. This is the I fault. So if I take the Z bus in and write it in the matrix form, what is happening is, so see what do I know? So this is V1, V2, so up to Vk, up to Vn. Is equal to Z bus into I1, I2, Ik up to In. This is simple Ohm's law for the network. So this we have seen many times. This is nothing but voltage vector. This is nothing but Z bus. This is nothing but current injection vector. Current injection vector, that is external currents. So now the question is, this fault current IF which is coming out of this bus, what is the source of that current? From where is that current coming? So we are talking about external currents. So there is a ground here. So from ground the current comes because this current is anyway going into the ground. And the ground current may not enter like this. So there may be a generator at bus N and the other end of the generator is grounded. So from that again the current goes into the network. So like that the current can go into the network from any part of the network which is grounded. Finally it comes here. So strictly speaking, since we are not worried about the external currents for the other buses, so I can write something like this. So I can, the only change will be if there is a fault at bus K, then I'll get, so I can just simply take the delta for this, that is delta V1 to delta Vn is nothing but, the Z bus is same, here the delta In. So I1 doesn't change, I2 doesn't change and so on, only the Ik will be subtracted by minus If. So, or in fact I should not even write Ik here, this is minus If because I am just writing the delta K. So like this you will get it. So from this you see these are all zeros, there is no change in the other. So you can say there is a change in the ground current here. So, but the ground current is not included in this matrix, so we don't have to worry about that. So, only this minus IF is coming here. So, what happens now, because all the other columns are 0, then this delta V1, delta V2 and so on up to delta Vn, what happens to this? So because this is 0, so the first column elements will get multiplied by 0. The second column elements will get multiplied by 0 and so on. So only the kth column elements will be available here for multiplication with minus IF. So I'll write it Z bus k column, kth column. Only that will be multiplied with minus IF. And finally, so this is now an individual element, it is multiplying with all. So therefore, delta V1 will be Z1k into minus IF. Delta V2 will be minus Z2k into IF and so on. Delta Vn will be minus Z3k, sorry, Znk into IF. That means this is important formula. So to know the change in the voltage, you just multiply that column of the impedance matrix with the fault current and you can get it. So if you have the bus impedance matrix, I can find out the changes in the voltages. So that is the summary, or that is the conclusion of our analysis or derivation of the last 10 minutes. So this is the derivation. So what I have done, just some how to find the, so this is nothing but changes in post-fault voltages. In other words, exactly what then? What is V1 then? So V1 post-fault will be equal to V1 plus delta V1. So what was it? This is pre-fault. Whatever was the pre-fault one, that I have to add this. So we have to just look at the sign, because if there is a minus here and then IF itself is minus, then we'll have to adjust that properly. So we know that the post-fault voltage will be less than the pre-fault voltage by magnitude. So that's enough for us to judge the sign. Anyway, let's do a problem. Let's do a problem on this. So the problem is like this. So again, I'm using the Hadis Adar's book to illustrate this problem. The problem is like this. For a 4-bus system, Z bus is equal to, J is outside, so J into 0.24, 0.14, 0.2, 0.2. So it will be symmetrical. So I'll just write like this. Then 0.2275, 0.175, 0.175. So this will be 0.175 and 0.175. And this element will be 0.31, and here also 0.31, and here also 0.31, and finally 0.5. So imagine that for certain power system, this is the Z bus. So directly Z bus is given. So the long method is, I give you a small network, 4-bus system, then you find the Y bus, then you invert the Y bus, finally you get the Z bus like this. Now the question is, like this, part A. A bolted 3-phase This is A. Fault occurs at bus 4. Determine fault current and post fault voltages. So this is the question. So now if there is a fault at bus 4, what is Thevenin's impedance of bus 4? We already know, look at the matrix, the 4 by 4 matrix, this is Z44. Thevenin's impedance at the bus 4 is 0.5. So therefore, the fault current will be 1 per unit is the fault voltage. So divided by Z44. So that is nothing but 1 by 0.5. So this J is also there. J is outside, so I just brought it in. So minus J2 per unit. So this is the fault current. Now once I got the fault current, what are the changes in voltages? Delta V's are nothing but. So which bus is the fault? Fourth bus. So you take the entire fourth column, that is 0.2, 0.175, 0.31. So 0.2, 0.175, 0.31 and 0.5. This one you multiply by minus J2. So this is, by the way, the meaning of bolted three-phase fault is the fault impedance is 0. That means Z fault equal to 0. Okay, so now if I do this, I'll get the delta V. So what is that? So minus J2 into 0.2 is minus J 0.4. And so by the way, these are all also having J's. So J into J is minus 1 and the minus will get cancelled. So this is, actually I have to delete this J. And then 0.2, sorry, 2 into 0.175. So 17.5, I think it is 35. So 0.35. And then 0.31 into 2 is 0.62. And then 0.5 into 2 is 1.0. So these are the delta V's, change in the voltage. So I think here it should be a minus sign. Okay, so now I got the delta V. So what is the post fault voltage? So here I'll get the post fault voltages is nothing but pre fault voltages, that is 1 per unit, 1 per unit, 1 per unit and 1 per unit minus delta V. So the V1, V2, V3, V4 after the post fault will be like this. 1 minus 0.4 is 0.6 per unit. 1 minus 0.35 is 0.65 per unit. 1 minus 0.62 is 0.38 per unit. And finally, this is 0 per unit. So because there is a fault at bus 4, the bus 4 voltage falls to 0. Bus 3 voltage is 0.38, bus 2 voltage is 0.65 and 0.6 and so on. So this is the post fault voltages. So I hope you got this problem. So the problem is simple. A 4 bus system bus impedance matrix is given and a fault is given at bus 4. Therefore, when there is a fault at bus 4, I get the fault current, and once I have the fault current, I can multiply with this and then I find the voltages. So I hope this is easy to follow. So any doubts you have up to here? I'll wait. So the question is like this, just a brief modification of the previous thing. So the question is like this. A three-phase fault occurs at bus 3 with fault impedance ZF is 0.19, I'm sorry, 0.14 per unit. So this is the fault impedance. Determine fault current and post fault voltages. So now you see bus 3. So therefore you take the bus 3, that is 0.31 is the Thevenin's impedance of the bus 3. So therefore the fault current will be the voltage, that is V3 post pre-fault divided by Z fault plus Z33. Now in earlier case it was a voltage short circuit fault, so Z fault was 0, but here we have some finite value. So this is 1.0. Now the fault impedance is 0.14 with J and Z33 is J 0.31. So this will be 1.0 divided by J 0.45. So how much will that be? So we get J 2.22 per unit. So this much is the fault current that we are getting now. So that is the first part of our solution. And once I have the fault current, so how to find the post fault voltages? So delta V is nothing but Z bus third column. So I take the third column of the Z bus and then multiply it with the fault current. So what I get, what is the third column of Z bus? So that is nothing but J into, if I look up, 0.2, 0.175, 0.2, 0.175, then 0.31, and finally the last element also 0.31. This one, if I multiply with minus J, 2.22. So this multiplication, so J into J will be minus 1 and this minus will get cancelled. So finally I'll get delta V to be, so let me do individually. So 0.2 into 2.22. So that will be 0.444. For the second one, 0.175 into 2.22. That will be 0.388. Then 0.31 into 2.22. That is 0.688. And the last one also will be the same. So these are the changes in the voltages. So therefore, post fault voltages, nothing but V, nothing but the original voltages, that is 1 per unit. So by the way, if the load flow solution is given and the voltage values are given, we should use that values. But if the information is not given, we'll take the original voltages to be 1 per unit minus delta V, whatever is delta V we have here. So finally that voltages will be, so what is 1 minus 0.444? So I get 0.556 and 1 minus 0.388, I get 0.612 and 688, 0.312 and 0.312 per unit. So this is my post fault voltages I am getting. So you notice that even though there is a fault at bus 3, the post fault voltage is not completely becoming 0. It is 31.2% of the original voltage. So therefore it's not going to 0. That is because some finite bus impedance, the fault impedance has been assumed. So I think with this I'll end this problem. let's look at some more interesting concepts later. But meanwhile, I'll just wait for a minute. You have any doubts? We can ask on this problem. Or the Thevenin's impedance. So let's see what I mean. So the short circuit current. So that is ISC in amperes. So let's look at the magnitude itself in amperes. So not just in per unit, I have also converted and now I got the short circuit current in amperes. Now the question is, what is short circuit MVA? So SC I am using short circuit, MVA. So SC means short circuit. So let me mention it here. So this is SC. So short circuit MVA. So you know that if you want to know the complex power, so short circuit MVA will be nothing but root 3 into rated line voltage into short circuit current in kiloamperes. So how to get kiloamperes? So because this is rated VL in kVA into short circuit current in kVA. So how in kiloamperes. So kilo into kilo will become mega. And this is just kV. Voltage I want in kilovolts and current I want to express in kiloamperes. So then I get the short circuit MVA. So how to convert the actual amperes into kiloamperes? Just divide by 1000. So whatever actual short circuit current you get, divided by 1000, then you will get the short circuit current in kiloamperes and rated voltage in kilovolts, and then root 3, then you will get the short circuit MVA. Okay, that is good. So we also know that S base. So S base MVA is nothing but root 3 into rated voltage in kilovolts into I rated in kiloamperes. So for that also you divide by 1000 because rated current will be in amperes. So if I divide these two, so what is the short circuit MVA divided by base MVA? This is nothing but short circuit in per unit. Short circuit MVA in per unit. Let me write it here. Because actual quantity divided by base quantity will be per unit is equal to, so here what happens, root 3 gets cancelled, rated voltage will get cancelled, the 1000 also will get cancelled. I'll just have ISC by I rated. This is nothing but I short circuit in per unit. So therefore, so finally what is the conclusion? So interesting conclusion is like this. So this is conclusion number 1. Short circuit MVA in per unit is nothing but short circuit current in per unit. So therefore, if my short circuit current is 3 per unit, that means the MVA rating will be 3 per unit MVA rating. So in other words, so take for example, let's say there is a transformer. There is a transmission line, there is a circuit breaker, and then there is a transformer. Now, or let me write it like this. There is a transformer, then there is a circuit breaker, and there is a bus bar. Now this transformer is, let's say 50 MVA. And due to some reason, the fault current is, let's say, minus J3 per unit. That means, what will be the fault current carried by the circuit breaker? And what would be the MVA rating of the circuit breaker? So, therefore, short circuit MVA, is also nothing but 3 per unit. I am just taking the magnitude. So, therefore, the rating of the circuit breaker. So, this is circuit breaker. So, therefore, circuit breaker rating should be 3 into base MVA for the system, which is 50 MVA for example. So you will get 150 MVA. So that is the significance of this. So to protect a 50 MVA transformer, you have to put up a 150 MVA circuit breaker. So the circuit breakers are always, the larger capacity, because if the fault current is going, if the circuit breaker itself gets overloaded, it doesn't suit the purpose. The circuit breaker has to be large enough and capable enough to handle the fault current and interrupt the fault current. So that is the important conclusion from this. So this is example for conclusion 1. Now another thing is, so let's say conclusion 2. So what is fault current? Or what is short circuit current? Is nothing but 1 per unit divided by the ZTH, the Thevenin's impedance at that bus. So why it is like this? We are just assuming that the voltage is anyway rated voltage. So although it may be plus minus 5% from 1 per unit, we are just taking like this, and we are doing like this. So therefore, if this is in per unit and this is also in per unit, then the short circuit input current is nothing but the reciprocal of Thevenin's impedance. So this is another conclusion. So reciprocal of Thevenin's impedance is nothing but short circuit current in per unit, which is also nothing but short circuit MVA in per unit. So in one shot, I am getting 3 different informations. So for example, if I go to the top, a Z bus is given. If I want to install a circuit breaker at bus 1, so 0.24 is the Thevenin's impedance, 1 by 0.24 will be the fault current, and that will be the rating of the MVA rating of the transformer, of the circuit breaker. Similarly, here also it is like this. So now if I look at the entire thing, at bus 4, because the impedance is more, the fault current will be less, and the circuit breaker required will be smaller one. You look at the values, it's slightly reducing, slightly, of course here it is slightly reduced, but here it is slightly increased, and again slightly increased. So probably bus 1 and bus 2 are generator buses, so therefore their Thevenin's impedance is smaller, and therefore they are prone to larger faults. Whereas compared to bus 5, maybe bus 4 in the system, maybe a load bus, and it has a higher Thevenin's impedance, therefore the fault currents will be lesser. So if you compare the fault current of 3 and 2, so 1 by 0.31 will be almost 3 per unit, whereas this one is only 2 per unit, so fault current. And whereas this one, for the bus 1, the fault current will be 4 per unit, because 1 by 0.24 approximately 1 by 0.25, that is 4 per unit. So anyway, that's about the discussion I wanted to have on this. So any doubts on this? So this is interesting. So we have about 15 minutes of time. So what I want to do now is I'll conclude by just let me share page 4 on the topic of symmetrical faults. So let's do one final problem on the topic of symmetrical faults, and with that we will end this particular topic. So it will take about 15 minutes. So again, I have been mentioning many times there will be a chapter on faults analysis, and open that there will be a symmetrical fault chapter and there will be a chapter on unsymmetrical faults. So open that and then choose a good problem and then work it out and see, compare your results with the results given in the textbook. That way you will feel confident about this subject. So I think this is fourth or fifth question that we are doing today. So I don't remember the count. So but let's go with question 4. Okay, so let me take at least 5 minutes for explaining the question actually. The question is something like this. So I'll draw the consider following system. The system is like this. There is a generator. There is a generator here, and this generator. So by the way, if I before I go ahead, this is example 10.7 from Granger and Stevenson. So if you go to this power system analysis textbook by Granger and Stevenson, in that I am doing example 10.7. So there is a generator. Immediately following the generator, there is a circuit breaker. Then I have a transformer. Then there is another circuit breaker. Then I have a long bus bar. Sorry. Okay. So this is a long bus bar. For this bus bar, there are 4 motors are connected. So this is motor 1. So I'll write M to represent the motor. Then this is motor 2. This is motor 3. And finally there is a motor 4. So what are the ratings? The ratings are like this. Let me just highlight this bus bar. So 25 MVA. So this is 25 MVA. 13.8 kilovolts generator which has X double dash of 15%. So XD double dash is 15%. So this is the subtransient reactance is given, not the transient reactance, subtransient reactance is given of 15%. Okay. Then what else? Connected through a transformer to a bus which supplies 4 identical motors as shown in the figure. The subtransient reactance of each motor is 20% on the base of 5 MVA. So XD double dash is 20% on 5 MVA. But the voltage rating for these motors is 6.9 kV. So you notice that the line voltage at the generator side is 13.8 kV, whereas the voltage at the motor is small, slightly lesser voltage, 6.9 kilovolts. So anyway, let's continue. So these 4 motors are identical. So all 4 motors are identical. Okay, so let's continue. The three-phase rating of the transformer is 25 MVA, 13.8 by 6.9 kV. So the transformer rating is 25 MVA, 13.8 by 6.9 kilovolts. Okay, interesting. So there's no problem with adjusting voltages, it is convenient. With leakage reactance of 10%. So the leakage reactance is 10% for this particular transformer. Okay, that is also fine. The bus voltage at the motors is 6.9 kV when a three-phase fault occurs at point P. So this bus voltage V1 is equal to 6.9 kV. This is post fault or pre-fault, sorry, before the fault. So when I say 6.9 kV, I can assume that, or I can designate that as 1 per unit. So there is a point P. At that point P, fault occurs. So this is a three-phase fault occurs at point P. For the fault specified, determine the subtransient current in the fault. So what we have to find out is find subtransient fault current. What is subtransient fault current? That means immediately after the transient, how much is the fault current? Immediately when the fault has come, what is the fault current? All right. So this one, this circuit breaker, these are all circuit breakers. So this circuit breaker is called circuit breaker number A. So because that's required for the next question. Subtransient current in breaker A. Now the fault current I have to calculate, that is I fault. Whereas the fault in the breaker, so let's call it I capital A. So this is breaker A current. Now you can say the question, how come they are different? Fault current and breaker current should be the same, but in this case they are different. So what happens is, so let me map the fault currents. When there is a fault occurring here, the motor is also ultimately a rotating machine. So when there is a fault in the system, the rotating machine also will supply the fault current. Actually what happens, the fault current will start from the generator and then it will come like this. Through the breaker, it comes to the fault. So this is one. Another fault current will come from the motor 1 and goes into the breaker. Another fault current comes from the motor 2 and goes into the breaker. Another fault current comes from the motor 3 and goes into the breaker. So that way the breaker carries the fault currents coming from generator G1 and motors 1, 2, 3. Whereas motor 4 also sends some current, that current will also add to the fault. So the breaker current will be addition of current from G1, motors 1, 2, 3. Addition to that will be the motor current coming from motor 4 will be added to the fault current here. So this is the additional current. Okay, so that's the question. Find out the breaker current and this one. And finally, if I'm using a circuit breaker, what is the rating of the circuit breaker? Okay, so very quickly we have about 3 minutes left or 3 to 4 minutes left. So I'll conclude in that time. So I'll try to conclude. So I'll just do a little bit fast calculation. Please try to follow me. So first thing that you notice is 25 MVA, 25 MVA. These are all 5 MVA, all 4 motors. So first thing is you convert all 4 motors into common base, that is 25 MVA. So 5 MVA becoming 25 MVA, the reactance will be multiplied by 4 times. There's no problem with the voltage because we are anyway following the proper transformation ratio and all. So because, sorry, 5 times because ratio of this. So step 1 is converting motor reactance to system base. So XM is nothing but 20% multiplied by 25 MVA divided by 5 MVA. So I'm not using that VB formula here because the base voltage is anyway same. So this will go 5 times. So 5 into 20. So that is nothing but 100%, or that is nothing but 1.0 per unit. So I got the impedance. So now if I redraw the circuit with the ground here, so this is the ground. So this I have a generator and I have a transformer. Then I have the 4 motors. 1, 2, 3 and 4 motors I have. So these 4 motors are also connected to the ground. So this is 1 per unit, this is 1 per unit, this is J1 per unit. Whereas this one, if I go up, it is given in the question 10% and here 15%. So this is J0.15 per unit and J0.1 per unit. So I have the circuit like this. Now, it's important to locate the fault. The fault occurred at this point. This is my point P. So, what is the Thevenin's impedance appearing at point P? Thevenin's impedance appearing at point P, I have to see. So, these two are in series. So this is nothing but equivalent to. You look at all these things, this is equivalent to the point P is like this. Point P, there is a fault, and then I have one branch which is 0.15 plus 0.1, that is J0.25. Then I have 4 branches. Each branch is having, so, and then these are all grounded. So I want to find the ZTH now. So this is 1, 1, 1, 1. So I'm not writing J, J1, 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 J1. So this is all 4 ones is 0.25. 0.25 in parallel with 0.25 will be 0.125. So therefore ZTH is J0.125. Because time is less, I'm just doing fast calculation. Now once I have the Thevenin's impedance, what is the fault impedance? That is J0 given. It's a short circuit. So therefore I can now find the fault current. So fault current at point P will be nothing but 1 per unit divided by Thevenin's impedance, J0.125. So this will be minus J8.0 per unit. So 8 times the rated current will be the fault current. So that comes to a question, what exactly is the fault current? So fault current in amperes is what? So what you do is, so for that you find out the I base. So we know that S base is nothing but root 3 into VB into IB. So what is S base for that part of the system? That is 25 MVA. Is nothing but root 3 into what is V base? 6.9 kilovolts into I base. So therefore I base will be 25 divided by, this is MVA, divided by root 3 into 6.9 into kilovolts, or 6.9 kilovolts. So volts will cancel, kilo will go to the mega and give me a kilo amperes. So that is 25 by root 3 into 6.9. So let me use my calculator. 25 divided by square root of 3 divided by 6.9. So I am getting 2092 amperes. This is my base current. So what is the exact fault current? So I fault is minus J8.0 per unit, which is nothing but minus J8 into 2092. That is nothing but 8 into 2092. That is 16,736 amperes. This is a huge current. So this is this much current of fault current. This is fault current at point P. Now what is the fault current in the circuit breaker? So to find the fault current in the circuit breaker, So you have 1, 2, 3, 4 paths, and this is the fifth path. You can use the current division principle and then find out the fault current in this path. So, but then just a simple so by observation. So this is where your familiarity with power system will come into, or circuits will come into. Let's see this. See, I am having J 0.25 here. Then I have J1, J1, J1 and J1. Now this side is grounded, this side is grounded, this side is grounded, and this side is grounded. And then there is a fault here at point P. Now we already come to know or calculated that this is minus J8 per unit. So now you notice that 0.1, 0.1, 0.1, 0.1 all together will be 0.25, and therefore I have 0.25 on the left side and 0.25 on the right side. So therefore this current by observation will be minus J4, and on the other side J4 will be divided equally. So this is minus J1, this is minus J1, this is minus J1, and this also is minus J1. So therefore all these currents are adding up to give me the 0.8 per unit. So 4, 5, 6, 7, 8. But then circuit breaker A is just on the left side of point P. So therefore current in circuit breaker A will be nothing but 4, 5, 6, 7 minus J7 per unit. And if you want to know the rating, so rating of the circuit breaker, of course it is 7 MVA rating, or 7 per unit will be the rating. That is will be in MVA. So what is that is nothing but 7 into 25. So that is nothing but 240. Is that 245? 7 5 is 35. 7 2 is 14. So 175 MVA. So the circuit breaker should be of rating of 175 MVA in order to withstand the fault current that occurs at bus A, that occurs at point P. Anyway, so this is about the circuit breaker rating, and I can also find the circuit breaker current. So what is 7 into 2092? That is 14,644 amperes. So this is just the magnitude. So this much 14,644 is a huge current. That much amperes is the fault current at bus 4. So this is about how to find the fault current in a system. So whenever the system is given, draw the single line diagram, equalize all the per units into this one, find out the Thevenin's impedance, and once you have the Thevenin's impedance, you can find the system fault current and all this. The reciprocal of Thevenin's impedance is fault current in per unit, which is nothing but the fault MVA in per unit. So I hope with this we plan to conclude this topic of symmetrical faults. Next week we will see unsymmetrical faults. So I hope you'll review these lectures, you prepare, and you will come for the next lecture. Any doubts you have right now?